So, how many of you are speaking there? Very much for the welcome. I hope you follow me. If not, as we said, still what I'd like to talk about now is a thesis that I've been working on the last 20 years or so. And it's involved students, PhD students, and one master's student. And the list is found in the Desert, Australia. So here are the students that I've been working on. Been working So this is what it looks like. It's a fairly large. They vary a little bit in colour, grey, red. And they use sand frames. You have grass, and the grass is white, which is very, there's not a lot of it. It's very dry, and they construct burrows that they live in. I'll describe those. So, on the left there, you can see one of the burrows. So these burrow systems can be 20 metres across. You can have maybe 10 or 15 different openings, and they're around about a metre in depth. And the burrow systems are mainly constructed by the males, but they also get help. I'll show in a moment that they actually live as family groups. You have the two parents and the children that live within the burrow system, and they cooperate to build these very extensive, very large burrow systems. So they're quite deep. So the burrow systems go down to about 1 metre below the ground. One of my students today put a lot of work into measuring the temperatures, both within the burrow. She put data loggers into the burrow at different depths in the burrow system, and also on the surface as well. What she discovered is that the burrow systems are very, very effective controlling the temperature. So the lizard has a preferred body temperature somewhere around about 35 degrees. You can see that the temperature on the graphs, but the temperatures are quite extreme at this time. During summer, the sun is directly overhead. There's no water, no humidity, no trees to absorb the temperature, moderate the temperature. You can get surface temperatures up to about 80 degrees Celsius. So that's going to kill a lizard very, very quickly. So also, if you look at the top left-hand side there, and you can see the orange buttons. They're the temperatures that you have that the lizard has within the burrow system. So we also measure the temperature of the lizards themselves within the burrow system. And you can see how well they're buffered in the burrow system. So what the temperatures are kept more or less the same within the burrow system, even though the outside temperature varies. The other thing that I'll just point out now, on the far right-hand side there, see lots of poo. That's poo. They poo at the same spot. They've got a venue. So they poo at the same spot, and that's very useful for some of the questions that we ask a little bit later. On the left-hand side, you see those metal traps. We put the lizards within those traps. You can look at the distribution of the traps. Traps are the metal traps. That gives you an idea of how broad the burrow systems are, because all of those traps are situated at different openings. Now, these burrow systems are very extensive, and they also provide important habitat for lots of other species. And these are just a few of the species that we've found living within these burrow systems, usually when the lizards have left. But they provide important habitat for many species, including some threatened species. So the mammal that you can see on the top right-hand side is an endangered species. That's a mulgara. We actually found quite a few of those within the burrow systems. And a range of also get. So they're an important provider of habitat for other species in that environment as well. So the distribution, you can see here, it's quite a large area. We're talking about a few thousand kilometres, maybe 2,000 kilometres across. The dark colour there is the current distribution. The lighter colour is where they were once found. In some parts of their distribution, they're now extinct, functionally extinct, and the species is listed as threat. So we're hoping that we can help with the conservation management of this species. This is vulnerable or endangered. So why is it a threat? One of the key threats, one of the main threats is fire and a change in the fire regime. And in a moment, I'll talk about some of the research that my students are making in order to identify this as one of the so what she did was she carried out two different experiments. she carried out one experiment for the locals where she looked at 30 different virus systems and she carried out different types of fire, different types of burning, different types of fire in these plots and compared the difference over time in terms of whether the lizards stay in the virus systems and whether they breed. And remember I talked about the fact that they've got Bandiera. Okay, you can go and you can see there are fresh food there. You know, the virus system is occupied. But you also look at the tracks in the sand. So where the lizards found, this environment is mostly sand. And so you can very easily see if there are tracks and whether the virus is still occupied. But the main message is that when you burn the area completely, the proportion of virus systems that remain occupied, that find lizards living in, is much less, and also the breeding declines dramatically. So there's fairly clear evidence in the localized manipulative experiment that by at least the complete burns will not break the also looked at 114 different virus systems across a much larger scale and essentially found the same thing. And this is after 4 years. So after 4 years after the trial, she found that the virus systems that have been burnt completely tended to be unoccupied. So pretty good evidence that fire is one of the incredible processes for this. The other threat, cats. So in Australia, the fauna is not used to this sort of predator like cats. And they are a major threat for these lizards. And so my student investigated this as a threatening process. For example, among some of the predators, we've got cats, foxes, vultures, and dingoes, which is essentially a dog. Cats had a significantly higher number of lizards in their food. Okay, so there's good evidence that the cats are a threatening process. So because they're threatened, there is a lot of interest in recovering these populations. And there's a lot of interest generally, but also because a lot of these lizards are living in areas that are managed by Indigenous people in Australia. Traditional owners. And so the traditional owners, the Indigenous people, have a very close relationship with this lizard, and they're actively involved in the management of their conservation management. So, where does the genetics come into it? Where does the genomics come into it? Well, one of the key things that we want to find out are the levels of genetic variation that are in the different populations. Why are we interested in this? We're interested in this because the genetic variation is associated with the risk of extinction. There's a lot of work now that shows this. One of the earlier examples from 1998 butterfly was work by Centurion, and it looked at the effect of habitat fragmentation on this butterfly, and in the smaller fragments, where the genetic variation went down, the probability of extinction increased dramatically. See that on the right-hand side here. So you can see the probability of extinction is much higher. This example, when the heterozygosity, another measure of genetic variation, is much higher. So there's lots of evidence for that. So why is genetic variation important? Well, it provides the raw material for evolution, so the adaptive potential, the capacity, the way to change when the environment changes. For example, so that's one of the reasons that genetic variation is important when it comes to survival, at least in the long term. The other reason why genetic variation is important is to do with the problem of inbreeding depression. All inbreeding depression is a loss of fitness as a result of low genetic variation. When you have low genetic variation, what happens is just about every individual carries some deleterious alleles. So carries alleles that will cause some harm if they're expressed. Most of them are recessive or partially recessive, which means that they're only expressed as a homozygote. So when the genetic variation goes down, the homozygosity goes up, and more of these deleterious alleles, the alleles that cause a loss of fitness, become expressed as homozygotes. And that's inbreeding depression. And it's a real problem in small populations. So that's the other reason why we want to maintain genetic variation, or at least know something about the level of genetic variation in these. So low genetic variation, lots of adaptive potential, and problem of lower fitness for inbreeding. Of course, it's not only the genetic variation that's important, there's a whole range of other factors, environmental factors that are important when it comes to extinction. Small populations are vulnerable to much greater fluctuations in demography, birth rates, death rates, and they're much more vulnerable to environmental catastrophes. And these environmental predators, habitat loss, exploitation, whatever it is, they're obviously major contributors to extinction as well. And they work in conjunction with the issue of low genetic variation to result in this extinction vortex. Okay, so we were interested in getting information on genetic variation. So first we need to capture the lizard. I mentioned this a little bit earlier. We put the lizards in these little traps, Sherman traps, or Elliott traps. They're distributed around the burrow system. Sometimes we use the sorts of traps that Elliott traps. get the lizard to take a tissue biopsy from just the tip of the toe. And then we look at the genetic variation. And we can look at how the genetic variation is distributed across the distribution. And some of the earlier work showed that the different regions were clearly genetically differentiated with each other. So there's quite strong genetic divergence among the different localities. And that's shown across a number of different genetic markers. So we know that they're genetically different in different regions. Getting back to the very localized scales, on the top left-hand side there, that's the distribution of the kinship within individual burrows. It might be a little difficult to see, but on the y-axis there, you've got a measure of relatedness. So the kinship relatedness. You've got a measure of relatedness there, and essentially, most of the individuals living within a burrow are either full siblings or the parents to the offspring. Okay, so they're family groups. They're families of the lizards living within burrows. So the young live within those burrow systems with the parents for a few years until they mature and disperse. When they disperse, they don't tend to disperse very far. And on the top right-hand side there, that's a spatial autocorrelation plot showing the relationship between the relatedness between individuals and geographic distance. And you can see that it declines fairly quickly. In a burrow system, it's full sibling relatedness. And it quickly declines. And that's provides some evidence that there is restricted dispersal, restricted gene flow across fairly small geographic areas. So the distances that we're talking there are up to around 20, 30 kilometres. They're big lizards, so they have dispersal capacity. They don't disperse that far. And when we look at the dispersal, it tends to be male bias. The males tend to disperse it more than the females. So when we look at family groups, there's male bias dispersal. And the other thing, there's been some DNA work that's been done using environmental DNA. And that's been used to get an idea of what they're feeding on. They but mostly what they're the vast majority of what they're and often you find that burrow systems in very close proximity to the subterranean termite systems, termites that live. Okay, so I've pointed out the distribution to you. We know that the areas are genetically distinct. We're interested to know whether any of these populations have low levels of genetic variation. I've talked about why low levels of genetic variation are problematic for survival. So if we find low levels of genetic variation, what we want to do then is think about whether we can improve the levels of genetic variation within those populations by translocation. And if that works, then that's a new genetic material, increasing genetic variation. There's been examples, I'll show one at the moment, where seen quite a few examples where the vital rates, the population growth rates, have increased following. So we do have a population down the south distribution at one group, and that was rediscovered and thought to be extinct. I went and sampled it 20 years ago, and the population is in decline. It's very, very important culturally for people there. So that's one of the populations. I think might have low levels of genetic variation. Could be a population. Just a few examples. Genetic rescue, one of the first ones that was carried out, and it's literally a textbook example, is with the Swedish addicts. Snakes there. The figure below it shows the population, and you can see that it increases after the introduction of males, maybe more genetically diverse population. As an example. The other thing to consider, if you are moving individuals around different populations, is the relatively low risk that's stated, the low risk of outbreak. So this is when you move an individual from a population that is very genetically divergent, particularly if there are chromosomal differences, which means chromosomal rearrangements, then that can cause a loss of interest in any offspring. It's usually short-lived, but it can occasionally be a problem if the population is very, very small. So the other thing is so in summary of the genetic data that we've got so far to work on this, we've got around about 16,000 SNPs from, that's just 367 individuals, 450 individuals now. Update the slide. We've got one complete annotated genome sequence, and we're just in the process of fully sequencing from each of the populations. So we'll have whole genome from each of the populations. Some of the other genetic data as well, which is we've been working with CSIRO and many of the traditional owners, many of the indigenous groups of Central Australia. Then decide what population might need to have translocation with these data. So we measure the level of genetic variation. Here, one of the measures that is very useful is measuring the proportion of the genome that is homozygous. And this is something that you can do very effectively with these new whole genome data. So whole genome sequence data is becoming much easier to generate these data. It's becoming cheaper. So the first step data, the single nucleotide polymorphism data. If any of your geneticists are familiar with the single nucleotide polymorphism data, the cost, the obtaining those data is now about 25%. Getting the whole genome data now is about 4 times more expensive. That might sound like a lot, but you get lots of information from it. You need to get that information. And the cost is coming down. So if there is anyone here that is beginning their career in conservation genetics or landscape genetics, whole genome sequencing is the sort of data that you get. The question, how do we measure the area is length of homozygosity across the whole, or runs of homozygosity. And whole genome data is very effective. There's a lot of information here. The main point that I want to get across is that getting an inbreeding coefficient, which is that's the probability that you're going to receive the very same allele twice from a common ancestor. In other words, you're homozygous. So getting an estimate of F from the runs of homozygosity is much more accurate than all of the other measures that you currently use. And it's a very important measure if you're trying to decide a population, whether a population is at risk of increase. Yeah. So that's some of the data that we're going to be using to identify populations that might have implications. Once we've got that information, the next thing that we'll be doing is getting measures of kinship. So again, I'm just mentioning this information briefly in case there's anyone here that's interested in conservation genetics. I'm happy to talk about this later on. But kinship is a very good way of deciding on which populations are the best to select the translocation for genetic rescue. Essentially, kinship for any two individuals, you can obtain these measures using SNP data and the whole genome data. The inbreeding coefficient for offspring. So it's a very direct way of saying, well, which populations are best to mix. I don't have the data for this is yet, but these are very nice examples. You can use the kinship matrix to select the lowest kinship between populations, taking the population mean. The lowest kinship here is minus 0.4. And if you mix those two populations, it's a very large. So that's genetic risk. It's just an illustration of how you can use kinship as a way of selecting populations. Okay, so you identify populations at risk. What's homozygosity? Then measure kinship and decide on which population is best to mix. This is the measured data, and it's just giving you an idea of the levels of kinship in population. And of course, I mentioned before that they live in families. So we have to be very careful how we sample. So I've just included this as a message. You've got to think very carefully about the social structure of the animals that you're working with if you want to use kinship. So deciding which population you want to use. because you're likely to bias your estimate if you include a whole bunch of data. So we were very careful measuring pitch to only use one individual per borough. So we don't have that bias. So doing that, you can see that there's a lot of kinship in these populations. So the lines, network and the lines to the bar, 12.5%. So that's going to be cousin half sibling, sorry. So I mentioned this extinction projects before. You can't just think about the genetics in isolation. All these threatening processes, cats, fire, small populations that have the bunch of random effects on population size. So you've got to think about this in conjunction together. There's a lot to take. One of the approaches that we're working on is usually using simulations to decide how to carry out genetic rescue. You only translocate once, lots of times. How many individuals do you translocate for genetic rescue? And this is a demographic genetic simulation where we incorporate information on population size and genetics. And again, if anyone's interested, I'll talk about it in more detail later. But the main points are that demographically, if a population goes just a little bit below capacity, then competition is reduced and it's something good for fitness, and then the population bounces back. But if the population size gets below, so then you get these demographic fluctuations that cause the rate of population growth to continue to decline. So you've kind of got these two different is that when populations get very, very small, they tend to lose their genetic variation through damage and continue to lose their genetic variation. And then there's the problem that the homozygosity increases, and that increases the risk. These simulations incorporate the demographic and the genetic. We can get into some detail here. So one of the problems with small, one of the problems with small populations is the connection of lots of drift. Another problem is that selection is much less effective in small populations. The reason selection is much less effective is because you've got lots of random genetic drift. It overwhelms selection. And so what that means is that you've got a relationship between how much of a problem a deleterious allele is to your fitness. How much of a fitness effect is that to the deleterious allele? And what the effect of random genetic drift will be on the frequency of that. Okay, so if it's got a strong bit, it's liquid, it's going to get selected out, even if it's a very small population. So small populations will tend to remove a lot of those deleterious alleles, a lot of the genetic variation that's really damaging in the homozygote form. Selection will still remove that genetic variation, even if the population is very, very small. However, if the fitness consequence is very, very low, it's still not good, but it's very, very low, the frequency of those alleles can increase through random genetic drift. And they might even become fixed in the population because the random genetic drift overwhelms. Effect is great. And so in these small inbred populations, you often get all of these deleterious alleles fixed in the homozygote form, and that can result in depression. I've actually got empirical data on this, on the species that we've worked on near where I live in Australia, and sampled populations over 10 generations between them, and we're measuring the dynamics of these deleterious alleles. You can actually see the relationship between how deleterious an allele is assumed to be. Talk about that, and the likelihood that increase will be selected. So I think this is a very real process. There's not a lot of empirical data, but we can incorporate this into the simulations. It's important to think about how many individuals and how many times you transfer to keep the heterozygosity levels up, to prevent these recessive and partial recessive units expressed. And to talk about this in more detail. I'm not sure how many of you are geneticists. Very boring to talk about it at great detail. So you can ask me. And likewise, once we've got that information, so I talk about the simulations we can do, simulate what the outcome is likely to be by having multiple translocations versus single translocation, the number of individuals that we might translocate into each population. You can simulate that, have a look at the outcomes. And you can also think about the consequence, the role of genetic drift that I was just talking about, and how that results in the having more of these deleterious alleles in the population. And also the relationship with heterozygosity, because these deleterious alleles are only revealed or realized. Anyway, you can put all of that into a simulation. Measure the outcome. That's what we're looking at right at I'll keep this fairly brief, I think. Some of the work that my student today did was to measure the temperature in the biosystems, and then she made some predictions on what might happen under climate change. And one of the reasons that we wanted to carry this out was because there was a paper in 2010. And all the authors, other than the fact that they point to the species that I'm working. They said this species is endangered. It's endangered because of climate change. I didn't think it was true. The reason I didn't think it was true at the time was because the forest systems, I thought that wouldn't protect it to some extent. At least the temperature were predicted to happen. And so that was part of the reason that I looked at this. So, as I talked about before, in the forest systems, even though you get extreme temperatures, the forest systems do a very good job of maintaining a stable temperature for these lizards. Various climate change conditions. It's hard to know for sure. You really don't know for sure what the consequences are going to be. But at least the model here would know that the visits would be out for a greater period of origin of global warming. So, at the very least, there's no evidence, as far as I can see, that climate change is going to be for great. And there's certainly no evidence that I can see that it's a reason that great Australia. It's fine. There's some data there that I put together with respect to consequences of climate change on this. Just very, very briefly, I mentioned outbreeding depression before, the problem that if you move an individual from a population that is genetically very, very different, it could have fitness consequences. We do need to think about that in transportations. One of the things that we could do is we could look at the adaptive variation across the landscape. We will do that. We will have adaptive variation across the landscape. Use that to evaluate the risk of and also have to get an idea of economic offsets. How genetically incompatible individuals will be to climate. We'll have a look at it, but we really don't know whether it's useful information for conservation. So it's just something we you can ask me about that later on. And just very quickly to finish up, I mentioned at the start that this visit is very important for the Indigenous people of Australia. It forms part of their story. It's a very important part of their statues for the visit in some areas. And they're very, very interesting, the outcomes. So there are some impacts that this research is going beyond collecting the data. Traditional owners across parts of Australia. We've been learning from them a great deal about mine resources and lots of something about the way that my team's been carrying out science. So it's been a two-way learning. The last 20 years or so. So we've also been talks at schools malaria. So we're hoping that the communication of what the work that we're doing with it's both the scientific and social. That's as far as I want to go with the presentation. I hope that at least some of you understood. And I also just want to point to the textbook that was finished with very knowledgeable authors here. And this textbook, if you are interested in conservation topics, this textbook will be available about 3 weeks. Advertisement. Thank you very much. So that's what the simulations were for. More than one. It's going to be more than one. Some of the simulations have been done suggest maybe 3 or 4 translocations. Maybe usually translocate labs. Maybe it depends, but maybe 6 males 3 or 4 times over across the generations. There.
So I noticed that the habitat species like a savanna, right? Savanna.
Sort of. It looks like savanna. It's a bit dry and it's but it kind of looks like it because what looks like grass, well it is grass, but it looks like it's close to it.
Are there any threats for function like what's birds?
Yeah, it's a very good question. I can't but I think it's sort of so they need to have the right soil type to construct the soil deep enough. So you often get this slightly Australia, particular areas. I think some type of distribution is such so I think it's related to sort absolutely nothing. Actually, it's a good question though, because I said absolutely nothing. But one of the populations is there's a big rock in Australia, and it's very popular. There's a big road that goes to this big rock, and it goes right through the middle of the population. So it's to that road is it's dead on the road. It's big, I mean, huge, barrier, and certainly across the whole distribution. There's Australia is the least densely inhabited continent on the planet. On average, there's 2.3 people per square kilometre. Most of those live on the east coast. The central part, Australia, you can drive thousands of kilometres on serious sort of where it is preserved. It's very difficult to preserve, but there's no structure there.
Are many colors of the species has many colors. And the populations are like in one color. Or they are mixed.
They do mix. You do get
So for the transportation, they will keep the same. Or they
it probably depends. It's a very good question. It probably depends. Some of the populations have more. The single populations of red and so I'm not sure, when it comes to transformation, I think we'll probably be mostly using the genomic data rather than using colour as a guide. It's a good question. Thank you.
Pelo que parece que as populações são bem distintas, geneticamente. Mas para elas serem tão distintas, tem que ter uma coisa. Se fazer essas translocações, será que se ela pega a população vermelha, joga para amarelo, mas a vermelha vai pular sempre. Sempre se programar um lado da amarelo. Que estrutura é muito geneticamente. Muito distinta. Mas são diferentes locais. E cada local tem a sua morte. Cada local tem a sua.
Você mostra por isso? Grupos diferentes. Como vocês estão?
Então,
Perhaps that would be it's a very good. It probably is. It's a very good. Probably leaders of the process. What you're asking is start moving things around. So, well, that's our impression. Substantial enough. But if it's not substantial enough that it's going to cause outright depression for a choice, to say, hey, this is evolutionary legacy. We just live that this one's going to extinct. Or you have the transportation. In my view, the transportation, it's probably going. Otherwise, it's just historical record. So sorry, I found that quite difficult to hear. So what was the? I'm sorry. But yes, the principle analysis is effective in illustrating the differences. But you're right, it might emphasize. I take it. But there's quite a few analyses that show the same linkings. Respondeu o seguinte, ele só defendeu para qualquer uma coisa que na minha verdade foi muito mais, tá? in which complexity is your story is about mostly that's so the lists are very good at defending the barriers. They invest a lot of but every now and again a large partner comes along. It becomes something that barriers goes in there that eats the lizards and that's the risk going. So that can happen. But usually what happens is fire goes through, the lists go. We don't know exactly what happens yet. So the data, a complete burn, the lists go. In other species. Good question. Ya está.